Hello, multivariable kids. Let's do some normal and binormal vectors. Look at that drawing. Oh my gosh. All right, unit tangent vectors. You've seen those before, right? You know what that is. I'm traveling along a curve here, and I'm moving along my curve. I stop for a pause at point 1 for a second, and I draw a tangent line. Right, and the tangent line kind of talks to me about my position, right? My position, what's happening right at that instant, the instantaneous rate of change, right? What's happening there. If I keep moving along here, my tangent line is different, right? First one was pointing up more to the right. Second one's still pointing up, but moving a little left. And look what my position is doing. Rising, but curving out to the right and then back to the left. The unit normal is a vector. The unit normal vector to the curve is perpendicular to the tangent, and therefore perpendicular to the curve as well. And it talks to me, since it's the derivative of the tangent, it talks to me about what my tangent lines are doing, right? That's analogous to first, right, or single variable calculus, right? When you take a derivative, the next, or the derivative of the derivative, tells you about the behavior of the first derivative. So what's the deal with the binormal? Oh, sorry, I forgot the notation. A binomial vector, that's that third vector. Now look at that. First, I want to talk about a plane. There's a plane that contains the normal and the tangent, right? The binormal is the cross product of the tangent vector and the normal vector, and therefore is perpendicular to both, and therefore perpendicular to this plane. And I kind of think of the binormal as nailing down that plane that's traveling along with the tangent and normal. So if you can imagine, if you were traveling around a circle, if you just had a flat circle in space, right? Your tangent and your normal, then you'd have a binormal here. Here's this little plane. You're traveling around the circle. That plane stays perfectly flat, and that binormal stands up straight all along this circle. But if you've got some kind of curve in space, right? How are your tangent and normal vectors moving in conjunction around that curve? And then now this yellow plane, it's not staying perfectly flat, right? Imagine you're imagining that. Right? It's going to go, that plane is going to tilt and swerve, and sometimes be steep and sometimes be flat. That normal, that binormal, being the cross product of the two, just helps me watch what that plane is doing. So these three vectors together help me think about the motion of the space curve, what's happening along that space curve. So the tangent vector, again, talks to me about the direction in which the curve, the position is going. The normal talks to me about the direction in which the tangent is moving, the first derivative. Then there's a special name called the osculating plane for that plane that contains the tangent and the normal. Osculating is actually a Latin word, has a Latin derivation or something. It means kiss in Latin. And it's because it's the plane, it comes closest to the part of the curve near the point. And then the binormal vector is perpendicular again to both. And I think of it as nailing down the osculating plane. There are actually two other planes too, the normal plane and the rectifying plane. But the osculating one is the most important. So let me do, I've done a lot of talking. I've tried to describe these. I don't do a very good job. I certainly can't draw. So let me go to a couple of applets and see if I can do a little bit better job. All right, here is some curve in space with a tangent line drawn to it. And as I move through time, you can see that tangent line moving along the curve, right? And you can see the tangent line changes, right, along, tells me what's happening with my curve. What's my curve doing? My curve is going to the right and going up, going more up, getting almost vertical. Now it's curving to the left, and then just kind of flattening out, right? Well, at that same time, what is the normal vector doing? The normal vectors tell me what are my tangent lines doing, right? Where are they pointing? Where are they going? Right, do you see that there? And then the osculating plane is, again, said the plane that contains these two vectors, kind of the plane of acceleration almost, right? And do you see how it flips and moves, right? Sometimes it's steep, sometimes it's more flat. Right? But as I try to picture that movement, the binormal vector is the one that really lets me see, oh, what is exactly that plane doing? So we do also have the normal plane. The normal plane has the two normal vectors in it, the normal and the binormal. This is called a normal plane because, look, can you see how the curve kind of like crashes right through it, goes through it normally, perpendicularly? See that? In the rectifying plane has the tangent vector and the binormal. Right, kind of more moves along with the curve, I would say, as opposed to, right, tangentially. Here's another one. Right, can you see? There's the curves, there's the three vectors traveling along. Right there now, they're all three the same color. So there's kind of, can you see? Can you tell who's the normal, who's the tangent, who's the binormal? Well, when I turn on the osculating plane, right? Can you see? It's easier to see, right? Can you see the two vectors that the plane contains and the one vector that's right? And do you see how that plane moves? Right? As it's flat, flips. The perpendicular plane, or the normal plane, now can you see how that contains, right, the two normal vectors? So who's kind of nailing this plane down? Right, and can you see how this one is, right, normal to the curve? Right, so I hope a little bit better than my pathetic drawings. All right, let's do an example here. So I want you to find the tangent, normal, and binomial vectors, and then I'll give you a value that I want you to compute them at. So let's start with the tangent. So it is the first derivative of position over the magnitude of the first derivative. Now look for some nice trig stuff to happen. Right, can you see what's going to happen here? This is going to be 9 cosine squared plus 9 sine squared plus 4 squared. I'm going to factor out the 9, and then I'm going to have cosine squared plus sine squared, which is 1, and 16. So that's the square root of 25. So I end up with and then the normal, it's like the second derivative, right? Ooh, you always like to see a 0. Now can you see what's going to happen here? I'm going to have 9 25ths cosine squared t, 9 25ths. Whoops, that should be a sine, shouldn't it? Forgot my fifths there. Gosh darn it. Right, so I'm going to have 9 25ths parentheses sine squared plus cosine squared plus 0 squared. So I'm going to end up with all on top of 3/5. So you can see these 3/5 are going to all cancel out. So I'm going to be left with negative sine t, negative cosine t, and 0. Now, what is the binormal? Remember, cross product is not commutative. It is the tangent crossed with the normal. So just be careful with your math here. Again, love to see the zeros. So 0 minus negative. 0 minus negative. And now what's going to happen here? 3/5, negative 3/5 cosine squared minus positive factor out a negative 1, and you're going to have that 3/5 there, right? Don't forget you have this negative out here. All right. So there's our tangent, our normal, and our binormal. And now I want you to evaluate them all at pi over 2. Actually, let's do r of pi over 2. right? There's my position at pi over 2. My tangent vector at pi over 2. And my normal at pi over 2. Oh, my pen is being so weird. And my binormal at pi over 2. Well, it's hard to see, isn't it? Sorry. Right down here. Okay, so again, some of this homework is, I apologize in advance, is a little algebraically hairy. Don't be afraid to check out Slater, right? And see when you get stuck, especially when it's with the algebra, go see some algebra tricks, right? They are not normal to people. They don't just naturally occur to people. Somebody had to show somebody else how to do it. So it's okay if you have to see and get help either from your peer or from a website or whatever to do the problem. Just make sure that at some point you redo them yourself and see if you can do them on your own from scratch. With that in mind, I want to talk a little bit about some algebra that's going to happen to you in 19A. In the process of doing number 19A, when you're asked to find the tangent normal, you are going to come up with and need to evaluate r prime of t, the magnitude of it, and, oops, sorry, you're going to get to an expression like this, and it is not going to occur to you to factor out an e to the negative 2t. It's just not. But I'm going to show it to you. If you divide everybody here by e to the negative 2t, look what happens. I divided every term by e to the 2t, and I balanced it out by multiplying by e to the negative 2t. This e to the negative 2t, I moved up to the numerator, moved this one up to the numerator, and this, of course, was 1. Rearranged some terms, thought of this as e to the 2t squared plus 2e to the 2t plus 1. This is a perfect algebra 1, perfect square trinomial. And then I'm going to be able to factor this beautifully. And now I have the square root of a product. And this is actually e to the negative 2 squared times something else squared with the square root. That will undo and get me that. Okay. Kind of cool algebra. So again, I apologize in advance for some of the nasty problems, but it'll make you stronger, right? See ya in a couple days.